Hi, everyone. I hope you're having a great holiday season. Welcome to December. I'm Nanette with Bridges Helena Community Connections, and I'm here to present this month's Cranium Cafe program. These talks will be posted every month on the Bridges website found at bridgeshcc.org or on the Bridges Facebook page. I will also send out a Cranium Cafe Brain Builder packet of fun puzzles to anyone who requests them, either by sending us a message through the website or via Facebook Messenger with your name and address. Please rest assured we are not selling your information to anybody. You are also welcome to pick up a Brain Builder packet at Covenant United Methodist Church, located at 2330 Broadway, across the street from St. Peter's Emergency Room. The Brain Builders are in a container placed on the left outside the front entrance of the building. Our Cranium Cafe talk today is based on the book Welcome to Your Brain by Sandra Amit and Sam Wang. Today's program is titled Accounting for Taste and Smell. So, animals are among the most sophisticated chemical detection machines in the world. We're all able to distinguish thousands of smells, including, just to name a few, baking bread, freshly washed hair, orange peels, cedar closets, chicken soup, and Forest Service outhouses on hot summer days. We're able to detect all of these smells because our noses contain a vast array of molecules that bind to the chemicals that make up smells. Each of these molecules, called receptors, has its own preferences for which chemicals it can interact with. The receptors are made of proteins and sit in your olfactory areas, kind of those membranes on the inside surface of your nose. There are hundreds of types of olfactory receptors, and any smell may activate up to a dozen of them at once. When activated, these receptors send smell information along nerve fibers in the form of electrical impulses. Each nerve fiber has exactly one type of receptor, and as a result, smell information is carried by thousands of these labeled lines that go into your brain. A particular smell triggers activity in a combination of these fibers. Your brain makes sense of these labeled lines by examining these patterns of activity. I'm going to take a break right now and talk about sneezes. So did you know that as many as 1 in 4 people in the US sneeze when they look into a bright light? This photo sneeze reflex appears to serve no biological purpose whatsoever. Why would we have such a reflex, and how does it work? The basic function of a sneeze is fairly obvious. It expels substances or objects that are irritating your airways. Unlike coughs, sneezes are stereotyped actions, meaning that each occurrence of an individual person's sneeze follows the same course over time without variation. The explosive beginning of a sneeze expels air at remarkable speeds, up to 100 miles per hour. A powerful, synchronized, reproducible event like this can only be generated by positive feedback within some circuit somewhere in the brain, one that leads to a runaway burst of activity reminiscent of the onset of an epileptic seizure. However, sneezes are different in that they have a preset mechanism for ending, and they don't spread in an uncontrolled way to other bodily movements or activities. The sneezing center is located in the brain stem in a region called the lateral medulla. Damage to this site causes us and other mammals to lose the ability to sneeze. Usually, sneezing is triggered by news of an irritant that is sent through brain pathways and into the lateral medulla. This information comes from the nose to the brain through several different nerves, including the trimengial nerve, which carries a wide variety of signals from the face into the brainstem. The trimengial nerves, well, we have one on either side, are cranial nerves with multiple functions. They process noxious and tactile stimuli from the face and much of the scalp, as well as from the conjunctiva and cornea of the eye. The trimengial nerve even carries motor signals in the opposite direction out of the brain, including the commands to bite, chew, and swallow. It's a really crowded nerve pathway. This crowded arrangement might explain why bright light could erroneously induce a sneeze. A bright light, which would normally be expected to trigger pupil contraction, might also spill over to neighboring sites, such as nerve fibers or neurons that carry nose tickling sensations. Bright light isn't the only unexpected sensation that is known to trigger sneezes. Has anyone ever had a gentleman sneeze after they've been intimate? Fundamentally, a crossed wire phenomenon like the photosneeze reflex is made possible because the circuitry of the brainstem is a jumbled, crowded mess. The brainstem contains critical circuitry for a wide variety of reflexes, including almost everything our bodies do. The basic layout of the brainstem was worked out early in the history of vertebrates. 13 pairs of cranial nerves are found in nearly every vertebrate, although fish do have 3 additional pairs that carry signals, such as those from the lateral line receptors along their sides. The cranial nerves that we have lead to a complex network of specific clusters of neurons or nuclei, which are basically arranged the same way and serve similar functions among all vertebrates. Indeed, looking at nervous systems in non-human animals is an extremely good way to guess how the structures in our brains work. The reason that brainstem structures are so similar across species is that the whole system is intricately constructed. From an evolutionary standpoint, it would be disastrous to move anything around on a wholesale basis. As successors to the earliest, simplest vertebrates, today's vertebrates, including fish, birds, lizards, and mammals, are all doomed to use a wiring layout that can be modified in small ways, but not fundamentally changed. It's reminiscent of the New York City subway system, which was simple at one point, but is now hopelessly convoluted after planners added layer upon layer of complexity. Some parts of the brainstem aren't used anymore, and the original core is now so jury-rigged and patched together that it can't possibly be replaced for fear of stopping the whole system cold. Frankly, the brainstem is about as good an argument against intelligent design as one could ever hope to find in nature. Now let's go back to our taste. So taste works the same way as the nose and the smell does, except that flavor receptors are in your tongue. Taste is simpler since there are only 5 basic flavors. There is salty, sweet, sour, bitter, and umami. So what is umami? It's the savory taste that's found in cooked meat or mushrooms or in the food additive MSG. There's no word for it in English, which is why we use that Japanese term. So each of these basic tastes has at least one receptor, sometimes more. Bitterness, for instance, is sensed by dozens of receptors. As animals evolved, they needed to detect toxic chemicals in their environments. Because toxic compounds came in many forms, it was necessary to have receptors that could detect all of them. This is why we have a natural repulsion to bitter flavors. This taste can be overridden by experience, though. Just look at everybody who loves tonic water and coffee. So why do we call spicy foods hot? The chemical that gives chili and hot sauce their zest is capsaicin. Your body also uses capsaicin receptors to detect warm temperatures. This is why you sweat when you eat spicy food. The receptors have what you might call a hotline into your brain to trigger responses to cool you off. You have capsaicin receptors not only on your tongue, but all over your body. One way to discover this is by cooking with hot peppers and then putting in a contact lens. Ouch. So, to finish up, we also talk about minty foods tasting cool for similar reasons. A receptor has recently been identified that binds to menthol. Plants may make menthol for the same reason that they make capsaicin, to make themselves taste bad to animals. Smells and tastes often have strong emotional associations. Your grandmother's apple pie or burning leaves in the fall, your loved one's shirt, fresh coffee in the morning. Smells can also have negative associations. On September 11th, 2001, in the days afterward, Manhattan was permeated by a bitter, acrid smell that nobody who was there can ever forget. Some smells may be negative for some and positive for others. Think about that line in the famous movie Apocalypse Now where the character of Kilgore says, "I love the smell of napalm in the morning." The whole hill smelled like victory. That's not pleasant to some people, but it was to him. These associations may occur because olfactory information has a direct connection into your limbic system, brain structures that mediate emotional responses. These structures are able to learn, raising the possibility that they allow you to associate smells with pleasurable or dangerous events. Thank you for joining us today. Come back next month, January, for our next Brain Builder program. And again, if you would like us to send you the Brain Builders, just let us know. Thank you.